Hello friends, so today we are going to do the questions from the year 2006, which is having one question, 2008 also one question, 2009 also one question, 2010 we are having 3 questions, and from 2011 the number of questions are 5. So total we are going to solve 11 questions. So in the first question, it was asked in the year 2006 and states that for spherical symmetrical charge distribution, variation of electric potential with distance from the center is given in the diagram. Given that the value of potential for R, which is less than R naught, less than equal to R naught, is governed by this equation, and for greater than R naught it is governed by this equation. And based on this we have to see which of these options is or are correct. So it can be multi-correct or single correct. Okay. So we are given 2 equations. So let me write. So we are given that the potential V is equal to Q upon 4 pi epsilon naught, and this is here 1 upon R naught, under the condition that value of R is less than equal to R naught. And the second equation is our V is equal to Q upon 4 pi epsilon naught and 1 upon small r, for the condition this small r is greater than equal to R naught. And the potential is also represented graphically, and in this graph we are given that as the distance from the center goes on increasing, for and y-axis represent potential up till the point where R is equal to R naught, the potential is constant, and after that it decreases almost exponentially. Okay, this decrease is not mentioned, but from here we can just draw one important conclusion, that when the distance from the center is you can say this R naught is the representation of the radius of that spherical conductor, whatever it is. Okay, it is only given that it is a spherical symmetrical charge distribution, so it must be considered a sphere, and that potential inside the sphere is constant, and after that it is going to decrease quite rapidly. Okay. And for option A, it states that total charge within twice R naught is Q. Okay. Total charge twice Q naught, total charge within twice R naught, sorry, is Q. Okay. And for twice R naught basically means that our equation number, let me name this equation 1 and equation 2. Okay. So for twice R naught, we can, our equation number 2 will be valid. So we can say for option A, it says that total charge within twice R naught. So from here we can say equation 2 is valid, And if equation 2 is valid, we can write that our V will be governed by 1 upon 4 pi epsilon naught, and this we can write Q upon R. And here we are given that our R is equal to twice R naught, or from here we can say this of R is greater than or equal to R naught. And this equation matches with the potential of a point charge Q which is located at the center, or we can say shell with a total charge of Q. You can say this equation is the representation of the potential of a point charge Q located at the center, or a shell with a total charge Q, or a shell of total charge Q. Therefore, from here we can draw a conclusion that total charge enclosed for R is greater than R naught, which is inclusive of twice R naught, is Q. So option number A is correct. Option A is correct. Then it states that option B states that total electrostatic energy for R less than or equal to R naught is 0. So for option B, our equation number 1 will be valid. Equation 1 is valid, and that states that our V is equal to 1 upon 4 pi epsilon naught Q upon R naught, and under the condition this R is less than or equal to R naught. Because in the question itself it is given the potential energy is for R less than or equal to R naught. So equation 1 will be valid. And from graph we can clearly see that our potential is constant. You can say from graph potential is constant up till r less than equal to r naught. Therefore, the electric field that is our E, which will be your minus dV upon dr will be equal to 0 because our V is constant. Okay. Based on this, we can easily find out our energy. So we can say energy, that is our U, and it is represented as half epsilon naught E square. Electric field is 0, so this gives us that our energy is equal to 0. So option number B is also correct. Option B is correct. Now it comes to at r is equal to r naught, electric field is discontinuous. Okay. So option C. And if we you can say understand the discontinuity with respect to electric field at any surface, it basically implies that the surface charge density at that particular point or at that particular surface is going to exist. Okay, this is the meaning of the discontinuity. So you can say discontinuity in the electric field at the surface implies a surface charge density exists. Surface charge density exists. We can also write it mathematically. Mathematically, we can write it as that our electric field outside minus electric field inside will be giving us sigma upon epsilon naught. Okay. But we know that our electric field E is equal to 0, which is basically inside, okay, because we just found out that the potential is constant inside, so therefore electric field is 0 inside. Okay. So we just found out that our E, which is equivalence of our E inside, is equal to 0. Therefore, we get outside can be written as 1 upon 4 pi epsilon naught q upon r naught square, okay, at any distance r. Okay. So which basically means that the field is discontinuous. So which means the field is discontinuous. Or we can say surface charge exists at r is equal to r naught. Surface charge exists at r is equal to r naught. Okay, because here we can find out this charge in terms of our surface charge density. Okay, we can use the formula Q and the surface charge density, that will be giving us sigma upon epsilon naught, because we have a sphere, hypothetical sphere for outside whose radius is r naught. Charge is given as Q and charge density is our sigma. So we can easily find out the relationship between the two, use it, and it is going to give the answer. So therefore the option number C is also correct. Option C is correct. And we come to the last part, and option D. And it says that there will be no charge anywhere except r is equal to r naught. And this can be analyzed based on the graph, and which states that there is a constant potential inside. Okay, so it means the only region with non-zero charge is the spherical shell, that is our r is equal to r naught. Okay, because there is no volume charge density existing inside. That's a direct relationship from the graph itself. So for option D, we can say that from potential behavior and constant potential inside, from the graph we can easily see that there is a, when r is less than equal to r naught, the potential inside is constant. Therefore we can say the only region with non-zero charge is spherical shell at r is equal to capital R naught. Okay. And from here we can also say no volume charge density exists inside. Therefore option D is also correct. Correct. Next question. It was asked in the year 2008, and it states that a nuclear charge Ze is non-uniformly distributed within a nucleus of radius r. The charge density rho dependent upon r, that is charge per unit volume, is dependent only on the radial distance r from the center of the nucleus as shown in the figure. The electric field is only along the radial direction. So we are given that we have a nucleus, obviously nucleus somewhat you can say spherical, something like this. And it says that it has a charge density that is rho of r, and it is only dependent upon radial distance from the center. So if this is radial distance from the center, so it is only dependent upon the r, and electric field is also in the radial direction. So based on this, we have these three questions, A, B and C, and graph is also given for our this charge density. We state that density is somewhat constant for this point r, sorry, this point is given as A, so it basically means at r is equal to A, and this point means when r is equal to capital R. Okay. And this charge density is having a constant value that is given as D for this graph is for r is less than equal to A, and for this graph we can say that our for that we have to write an equation. Okay, we will write that equation later on with respect to the slope. And so first it states that electric field at r is equal to capital R. Okay. We have to find out the electric field at r is equal to capital R. So this entire graph, charge density, can be represented in the form of a equation. Therefore, we can write the equation, the charge density that is our rho r, and we can write this in the form of equation. It is going to have a constant value D for 0 less than r and less than equal to A, and it is going to have a decreasing, and that a line equation which can be written as D multiplied by capital R minus small r and divided by capital R minus A, and this is when our A is less than R but less than equal to capital R, and finally it is going to have a zero value for R which is greater than capital R. So this is the equation for our charge density based on the graph. Okay. So here, which basically means that for this part the charge density is constant, value is given as D, and this is linearly decreasing, and decreasing towards 0, and it means that finally it will be having a 0 value. Okay. So for that we are basically going to use the Gauss law, and from Gauss law we can say using Gauss law at r is equal to capital R, okay, which basically means outside the full charge distribution. Okay. So which basically means outside the full charge distribution. Charge distribution, we can write the equation for our electric field. The electric field at a distance r will be equal to 1 upon 4 pi epsilon naught. We have this charge enclosed, and divided by our r square. So here the electric field at the surface depends only on the total charge enclosed in the sphere of radius r. So from here we can just draw a conclusion which is basically a representation of a Gauss law, and we can say that our electric field at the surface depends only on the total charge enclosed, only on the total charge enclosed in the sphere of radius r. In the sphere of radius r. But in this case we have to remember that the total charge enclosed is always ZE. For this particular case we have to remember that but total charge enclosed is always Z multiplied by E. Okay, because this is given the question, even though the charge distribution is non-uniform, but it still says that the charge is always ZE for this radius of R. So we can further write it that even though the shape of our density changes with A, which is from the graph, changes with A, the total charge is always fixed. The total integrated charge, integrated we are calling because it is a non-uniform distribution. Okay, so total integrated charge is fixed to ZE. Okay, and regardless of how it's distributed inside. Regardless of how it is distributed inside. Let us check now the options one by one. And for the first option, it states that electric field at R is equal to capital R. Okay. So from this discussion, we can so option A, we can say the electric field at R is equal to capital R depends only on ZE. Okay. Electric field at R is equal to capital R, or we can just, let's write the formula first. So we can say electric field at capital R is equal to 1 upon 4 pi epsilon naught. Here charge, that is our Q, is represented in the form of ZE and divided by R square. So this is independent of A. Independent of A. So therefore option A is correct. Oh, sorry, yeah, let me name them 1, 2, 3. So for first option A is correct. So this is our part 1. And part 1 option A is correct. Now we come to the part 2. And part 2 states that for A is equal to 0, the value of D, that is the maximum value of rho as shown in the figure. Okay, so we have to find out the maximum value of D. Okay. And so we already know the equation that our rho of R is equal to D, and we have that equation as dr minus R divided by R minus A. R minus R, and we have this is R minus A. And but here it states that at A is equal to 0. Therefore we can write the equation that our rho of R will be equal to dr minus small r divided by capital R. Now we can easily find out the total charge. So you can say total charge I suppose that is given as capital Q, and that will be our charge density, that is dr minus small r divided by capital R, and multiply by the, this will be our 4 pi r square multiplied by dr. And for the entire we are going to integrate it from 0 to capital R. So now it is a quite simple solution, and we can take some things as common, and okay, so this can be written as 4 pi d divided by R and 0 to capital R, and this comes as R minus R whole square, sorry, R minus R, and this is our R square multiplied by dr. And we are only interested in this integral, so let us solve it separately. And so for the integral 0 to R, R minus small r, and we have this as R square dr, this will be equal to, we can just separate it. This is our R 0 to R, and we have this as R square dr minus 0 to R, and here we have our R cube dr. So this is going to give us R, and this part will be our R cube lower and upper limit, so come as capital R cube divided by 3 minus this will be our 4, so it comes as capital R4 divided by 4. So this can be written as our R4 by 3 minus R4 by 4. LCM we can take as 12, so this comes as 4 minus 3, that is our R4. Therefore we can write that our total charge Q will be equal to 4 pi d R, and this comes as our R4 divided by 12. And we can cancel it, goes by 3 and this goes by cube, and we are left with pi d R cube divided by 3, and total charge we know is nothing but our ZE. Therefore we can write our ZE will be equal to pi d R cube divided by 3, and from here we can easily find out our D. So we get our D is equal to 3 times ZE divided by pi R cube. So the option is our 3ZE divided by pi R cube. So option number B is the correct one. Option B is correct. And for third part, it states that the electric field within the nucleus is generally observed to be linearly dependent upon R. This implies that. So in the question it is given itself that the electric field is only in the radial direction, and the charge density is dependent upon only the radial distance, which is our R from the center of the nucleus. So let us sort it out for part 3 rather. So part 3, we can say that our charge density which is our rho of R, and it is going to have two values basically. First value is our constant value of D, and this is from R is equal to 0 to R is equal to A, and then there is a linear decrease to 0, and this is from R small r to R is equal to capital R. Okay, this is given to us, and we are also given that rather in the part C it says that electric field within loop is generally observed to linearly dependent upon R. So from here we can write that electric field, that is our E of R, is dependent upon, suppose we call that as at a distance R. So we are given that our electric field inside is linearly dependent on R. Therefore we can write that our electric field with respect to R is linearly dependent upon our R. And therefore, with the help of Gauss law, we can say that from Gauss law, we can write that our electric field will be equal to 1 upon 4 pi epsilon naught, and this comes as charge enclosed, but this charge has to be within this radius r, and this is charge enclosed, and divided by r square. But for the condition that our electric field is directly proportional to our this r, we can write that for our E of r is directly proportional to r, therefore we can write our Q of r divided by r square is proportional to r, or we can write our Q of r is proportional to r cube. And this relationship, or we can say this entire analysis, is only possible if our, we can say this is only possible when our rho of r is equal to constant. In the region from r is equal to 0 and r is equal to capital R. And we have to find out, one second. Okay, so we have to find out this entire analysis with respect to A and capital R. So we can just modify it, and we can say that we can say we need to find out value of A. We can say value of A. This is required for the condition that our this electric field is linearly dependent upon R. Okay. And for this, we can say that our if A is equal to capital R, then we know our rho of R is equal to D, that we can write for the graph. Okay. Now we can just find out our charge density, that is Q of R will be equal to 0 to R, and we have this as a rho, and we have this as 4 pi R prime square, and this comes as R prime derivative. This R prime is little bit differentiation in order to differentiate between this given radius R and this rest is doesn't matter because it is a simple another variable, and this will be coming equal to as rho 4 by 3 and pi r cube. And from here we can easily say our rho of r is directly proportional to our r cube. Thus our electric field, which is our 1 upon 4 pi epsilon naught Q of r upon r square, this will be proportional to our r cube divided by our r square, which is proportional to our r. Okay, and this is the basic assumption in the question, that the electric field is directly proportional to our small r. Therefore, we can say that for E of r is directly proportional to r is true only if A is equal to capital R. Okay. So option number C is correct. Option C is correct. Next question. It was asked in the year 2009, and it states that a solid sphere of radius r has a charge q distributed in its volume with charge density rho is equal to k r raised to power a, where k and a are constant and small r is the distance from its center. If the electric field at r small r is equal to capital R by 2 is 1 by 8 times that r is equal to capital R, find the value of A. So here we are given the charge density. Charge density is given to us, that is our rho is equal to k r raised to power A. Okay. And in this case we are going to use our, you can say, Gauss law in order to solve it. Okay. And we are mainly interested in electric field, so we start with the Gauss law in order to find out the electric field, and we say that electric field at a distance small r from the center that is given as our E is equal to 1 upon 4 pi epsilon naught. We have charge enclosed and divided by r square, and we can easily find out our charge enclosed with respect to our charge density is rho is given to us. Therefore, we can say that our Q enclosed will be equal to, this is rho 4 pi r square dr, and integration is 0 from r. Rho is given to us, so we substitute its value. Rho is given to us as k r raised to power a, and this is 4 pi r square and dr. So we can take something as constant, so we get this as 4 pi k integration 0 to r, and this comes as r a plus 2 raised to power a plus 2 and dr. So this gives us 4 pi k, and we are left with this as r a plus 3 divided by a plus 3. Now we can easily calculate our electric field. So we can say that our E will be equal to 1 upon 4 pi epsilon naught. Charge enclosed we just found out is our 4 pi k, and this is our r a raised to power a plus 3 divided by a plus 3. and here our 4 pi cancels out, so this comes as k upon epsilon naught, and here r square is left, sorry, we also have its r square, so this r square and this cube will be sorted out, and it comes as r a plus 1 divided by a plus 3. And we are given that electric field at the distance of r is equal to r by 2 is 1/8 of at r is equal to capital R. So we are going to find out electric field at this particular point. So you can see electric field at small r is equal to capital R by 2. This gives us k epsilon naught, and we simply substitute the value. We get this as r by 2 whole raised power a plus 1 divided by a plus 3. And electric field at r is equal to capital R will be coming as k upon epsilon naught, and this comes as r a plus 1 divided by a plus 3, and the relationship between the two is by 1/8. So we can write that our electric field at r is equal to r by 2 is equal to 1/8 of 1/8 of electric field at r is equal to capital R. We simply substitute them. We get this as k upon epsilon naught, and this is our r by 2 whole raised to power a plus 1 divided by a plus 3 is equal to 1/8, and this is our k upon epsilon naught r raised to power a plus 1 divided by a plus 3, and this k epsilon naught a plus 3 cancels out, so we get this as we are left with this will be r a plus 1 divided by 2, a plus 1 is equal to 1/8, and we have a r a plus 1, and this a plus 1 and this also cancels out, so we get from here that 1/8 is equal to 1/2 raised to power a plus 1, and this can be written as 1/2 raised to power 3. This 8 can be written as, therefore we can say our a plus 1 is equal to 3. A plus 1 is equal to 3, which gives that value of a is equal to 2. So value of a is equal to 2. Next question. It was asked in the year 2010, and it states that at a time t is equal to 0, a battery of 10 volt is connected across A and B in the given circuit. If the capacitor have no charge initially, at what time does the voltage across them becomes 4 volt? Taking natural log of 5 as 1.6, natural log of 3 is 1.1. So we are given that initially the capacitors are uncharged, and then we are connecting a battery source of 10 volt, something like this. And at what time does the voltage across them becomes 4 volt? Okay. both of them in parallel, so it doesn't matter. So we are going to find out at what time the voltage across this capacitor will be coming equal to 1 volt. So this is nothing but indirect representation of a series combination of resistor and capacitor. Here resistor we can write as R equivalent and capacitor we can write it as C equivalent. Okay. So this is basically a, you can say, equivalence of this circuit. And we know that the voltage across the capacitor, which is charging through a resistor, this is given as V of any time t is equal to V naught 1 minus E, and this comes as minus T upon our RC. And for sake of simplicity, let us write them as R and C, much more easier. Okay. And we want that the voltage across capacitor at any time should be equal to 4 volt. Therefore, we can say that our V of t should be equal to over 4 volt at any time t. So we substitute it, and this V naught is our applied voltage, या maximum voltage. Applied voltage. Therefore, we can write that our 4 is equal to 10, and this is our 1 minus E, and this comes as minus T upon RC. And here this R will be a parallel combination of this, and here C will be the parallel combination of this. So we substitute them, we get our 10 is equal to 1 minus E, and this comes as minus T, and we have capacitance parallel, which will be equal to 2 plus 2, that is 4. Resistance parallel, which is same, that will be coming as 1. So it comes as 1 into we are left with 4 into 10 to the power minus 6, and we can just easily solve it because we are going to find out time t, we need to find out, and now it is quite simple. So this comes as 4 upon 10 is equal to 1 minus E, and this comes as minus of t 4 into 10 to the power minus 6, and we can write this will be coming as e raised to the power minus t 4 into 10 to the power minus 6 is equal to 3 by 5, and we can further write it minus t upon 4 into 10 to the power minus 6 is equal to natural log of 3 minus natural log of 5. 3 minus natural log of 5 value is given to us, and from here we need to find out our t. So we can say t is equal to 4 into 10 to the power minus 6. This comes as natural log of 5 minus natural log of 3. So we get our t is equal to 4 into 10 to the power minus 6. Natural log of 5 is given to us as 1.6 minus 1.1, and this comes as 0.5. 0.5 is 1 by 2. So this comes as t is equal to 2 into 10 to the power minus 6. Okay, so time we have to find out in second. Okay, sorry, this is mega ohm. Okay, so let me multiply it by 10 to the power 6. So these to cancel out, therefore we get time is equal to 2 seconds. Okay, ideally it should be here, it should be equal to as 1 into 10 to the power 6 because of the mega ohm, but we can just multiply it later on, which gives us that t is equal to 2 seconds. Next question, it was asked in the year 2010 and states that a uniform charge thin spherical shell of radius r carries uniform surface charge density of sigma per unit area. It is made up of two hemispherical shells held together by pressing them with the force F. Then F is proportional to. So we are basically having two hemispherical shell and they are having same surface charge density. For the sake of convenience, we can assume that it is positive. So it means here will be also positive surface charge density and here will be also positive surface charge density. So which means that both hemispheres are having same charge. So there will be a force of repulsion between the two in this direction. In order to hold them, we need to apply the force F, which is just opposite and equal to them. Okay, so this is basically the question that is mentioned. So first of all, we are going to find out what will be the electrostatic pressure, or we can say force per unit area, because we are given the charge surface charge density, which is nothing which is given as per unit area. Okay. Therefore we start from there only. We say the electrostatic pressure or which is nothing but our force per unit area. That is our P will be equal to our charge density divided by 2 epsilon naught. Okay, and this will be acting outwards like in this direction. So based on this we can find out the net force. Okay, so you can say net force trying to separate one hemisphere from the other, okay, because they are acting in opposite direction. So we can say net force trying to separate one hemisphere from other. Let us call that net force as our F prime, which will be equal to the electrostatic pressure P multiplied by the projected area. So this comes as sigma square 2 epsilon naught multiplied by pi r square. And this will be our F prime because it is held tightly. So we can say our F prime should be equal to F, which will be equal to sigma square 2 epsilon naught pi r square. So we can say our force F is proportional to sigma r square upon epsilon naught, which was asked. Only the proportionality was asked, and that comes as 1 upon epsilon naught sigma square and r square. So option number A is the correct one. Option A is correct. Next question. It was asked in the year 2010, and it states that a tiny spherical oil drop carrying a net charge Q is balanced in still air with a vertical uniform electric field of strength 81 pi into 10 to the power 5 divided by 7 volt per meter. When the field is switched off, the drop is observed to fall with a terminal velocity of 2 into 10 to the power minus 3 meter per second. Given G is 9.8, viscosity of the air is 1.8, and density of this, find the magnitude of Q. So this question is basically into two parts. In the first part, it says that the charge is balanced in air by a uniform vertical field. Okay. So let us suppose we have a spherical oil drop and net charge on it is given as Q, and in the downward direction we are going to have mg, and it is balanced by the you can say the electric force that will be acting in upward direction. Okay. So this is our force due to electric, and that is nothing but electric field multiplied by charge Q. So this is our first case. Okay. So from here we can say that electric force is balanced by the weight of the oil drop. Electric force balance, or we can write electric force equal to weight, and our electric force is our E multiplied by Q, and weight will be equal to over 4 by 3, which is basically mg, and m we can write as 4 by 3 pi r cube multiplied by density and multiplied by g. So from here we can write that our charge Q is equal to 4 pi r cube rho g divided by 3 times our electric field. In this expression we know everything except the value of the electric field. Okay. And for that we can use electric field also given to us, and radius is not unknown here. Okay, electric field is given to us as 81 into this. So we need to find out this radius, and for that we are going to use the second condition when the electric field is switched off. So you can say when electric field is switched off. So in that case it is said that the ball, this drop is moving downward direction with a terminal velocity of, so this ball is moving in the downward direction with the terminal velocity, let us suppose this is our Vt. Okay. And in the downward direction obviously there will be mg, and in upward direction there will be a drag force. Sometimes it is also called as a viscous force. So in upward direction there will be a drag force, and the condition for the terminal velocity is that this drag force should be equal to our force which is acting the downward direction, that is our mg. So we can write for terminal velocity Vt, drag force should be equal to weight. And we already know the formula for the drag force, that is our 6 pi nu r multiplied by terminal velocity is equal to our weight, that is 4 by 3 pi r cube, and this comes as rho multiplied by g. And from here we are mainly interested in our, so this pi and pi goes away, and this goes by 2 and this goes by 3, and r goes by square. So we are interested in only r, therefore we can write our r is equal to, this comes as 9 nu Vt and divided by 2 rho g, and it's square root. So we are going to substitute. Let us call this equation number 1 and this as equation number 2. So using equation 1 and 2, from equation 1 and 2 we can write our charge q is equal to 4 pi rho g divided by 3 times the electric field and the value of r, that is our 9 rho Vt, this is 2 rho g, and this is 1 by 2, and this comes as 3 by 2. And we can just sort out it a little bit, not much we can do. We can sort out this rho g, this is 3 by 2 and this is whole raised power 1. So we can write this as 4 pi by 3e, and this comes as 9 nu Vt, and this is our 2, and we can write this as rho g whole raised to power minus 1 by 2. Not much we can be done, we simply substitute the values. So we get this as 4 pi, and this is our 3 electric field is given to us 81 pi divided by 7 into 10 raised to power 5, and we have here 9 multiplied by 1.8 into 10 raised to power minus 5, 2 into 10 raised to power minus 3 divided by 2, and this is given as 900 into 9.8 raised to power minus 1 by 2. So if you solve this, this q will be coming approximately into 8 into 10 raised to power minus 19 coulombs. Option number D is the correct option. D is correct. Next question. It was asked in the year 2011, and it states that a 2 microfarad capacitor is charged is shown in figure. The percentage of its stored energy dissipated after the switch S is turned to position 2 is. So this is suppose voltage V. Initially this capacitor is charged through the switch. Later on, the switch is moved to position 2, and then this 2 microfarad and 8 microfarad capacitor are connected with each other. And initially, it's not mentioned, but we presume that there is no initial charge on 8 microfarad capacitor. We have to find out the energy dissipated. So let's find out first of all the energy stored in the 2 microfarad when it is connected to V voltage source. So that will be our initial energy. Then we are going to find out the final energy and find out the percentage. So you can say that initial energy stored in the 2 microfarad capacitor initial energy stored in 2 microfarad capacitor, we can call this as U of I, which will be equal to half CV square, and we substitute the values. We get this as half 2 into 10 to the power minus 6, and we have voltage square, which comes as this 2 and 2 goes away. So this is our V square into 10 to the power minus 6 joules. And for this we can just draw the approximate circuit, and the circuit will be something like this. We have 2 microfarad and voltage source is V. And we can also find out the initial charge on the capacitor. So we can say initial charge Qi will be equal to C multiplied by V, and this comes as twice V into 10 to the power minus 6 coulombs. And then the switch is now on position 2. Switch is at position 2. So for that we can also draw an approximate circuit. This is our 2 microfarad. This is a switch, position 2, and now we have this as our 8 microfarad. And so there will be a transfer of charge from 2 microfarad to 8 microfarad until the potential becomes equal for both the capacitors. Or we can say till common potential Vc is reached. We can say that charge flows from 2 microfarad to 8 microfarad till a common potential is reached. Let us suppose that common potential is given as Vc, and we can easily find out the value of Vc, and this Vc will be equal to total charge divided by total capacitance. And total charge is our only initial charge, because 8 microfarad doesn't have any charge. Therefore we can write our Vc will be equal to 2V into 10 to the power minus 6. Total capacitance is our 2 plus 8 microfarad. That is our 10 into 10 to the power minus 6. And minus 6 cancel out. This 2 goes with 5. So we get our common potential, that is our Vc, is equal to V upon 5 volts. Therefore, we can find out the final energy, and final energy will be equal to energy in 2 microfarad plus energy in 8 microfarad. So we can say final energy stored in both capacitors, and let us call that as U of F, and this is our half. This comes as 2 plus 8, 10 to the power minus 6, and the potential is our V by 5 and its whole square. So this comes as 2 by 5 is our 10, 10 gives us 5, 5 goes with 5, and this is our 5 square, so we are left with only V square by 5 into 10 to the power minus 6 joules. Simple now. We need to find out the loss percentage loss, which will be equal to, let us suppose, delta of U, and this is our initial energy minus final energy divided by initial multiplied by 100, and we can just substitute the values. We get this as V square minus V square upon 5, 10 to the power minus 6, and divided by V square into 10 to the power minus 6. V square we can take common, so this comes 5 minus 1 divided by 5, and V square cancels out, so we get this as, and 10 to the 6 also cancels, so this comes as V square 5, this, okay, multiply by 100. This will be equal to 4 by 5 multiplied by 100, which comes as 80%. So option number D is the correct one. So this goes by 20. Option D is correct. Next question. It was asked in the year 2011, and it states that consider an electric flux E naught x unit vector, where E naught is a constant. The flux through the shaded area as shown in the figure due to this field is. So we are given the electric field that is in x unit direction. Okay, so electric field is given something like this, that is given as E. And we know our mathematically our flux is a dot product of electric field and area vector, and area is in our, you can say, xz plane. So we can just write the equation. So let us draw the basic. We know that our electric flux that is our phi is equal to our E dot A, and here from the figure we can see that the side of this shaded area is A. Okay, so therefore the area, you can say shaded area will be equal to A multiplied by A, which is our A square, and this shaded area we can say is in xz plane. Therefore, we can write that our vector, area vector, will be equal to a square x unit vector minus a square z unit vector. And electric field is given to us. We simply substitute them. We get that our flux phi will be equal to E naught x unit vector, and this comes as a square x unit minus a square z unit vector. And sorry, here it is dot product. So obviously x unit z unit vector will be equal to 0. So dot product is of x dot x unit, which will be equal to 1. So this comes as E naught a square. So therefore, option C is the correct one. C is correct. Next question. It was asked in the year 2011, and it states that 4-point charges, each of plus q, are rigidly fixed at 4 corners of a square planar soap film of side A. The surface tension of the soap film is gamma. The system of charges and planar film R is in equilibrium, and A is given as k q square gamma whole raised to power 1 by 1, where k 1 by n, where k is constant. Then we have to find out value of n. So we can draw a rough approximate figure that we have a soap film whose side is given as A. Side is given A, and each edge is having plus q charge. So each edge is having a charge of plus q. And it is also given that this system is in equilibrium. And so in this case, there will be tension of surface tension, or we can say the tension force, surface tension force rather, because of the soap film, and there will be a force of repulsion because of the like charges. And for equilibrium, they should be same. So first of all, let's draw, you can say, the electrostatic force at any one particular charge. So let us consider this charge. Okay. And the force, because let us call this as our A, this as our B, C and D. So force to D at B will be our this direction. Let us call this as FD. And because of C, force of repulsion, let us call this FC. And because of A, let us call this force of repulsion as our FA. And sides are given to us as A, so this distance will be square root of 2 times A. Therefore, we can write that our FA will be equal to k q square upon A square. Our FB will be equal to k q square upon A square, and we can write our FC will be equal to, sorry, not FC, but here it will be FC, and here it will be D, and FD will be equal to k q square upon 2 times A square. And so we can just let us draw this for point B. So this is our point B. We are having two forces. This is our FA and this is our FC. This, the resultant of FA and FC, will be somewhere in this direction. Let us call this as our F prime, and the same direction we are having a force of our FD. So the net force at point B will be equal to summation of FD as well as our F prime. So we can say that the total force at B, let us call that as F, will be equal to our FD plus, let us call this as F resultant, much more easier to understand, FR plus FR. And this FR will be our angle between the two forces is our 45 degree. So this will be our FA square plus FC square plus twice F1 F2 cos of 45. Okay. And or in the simpler term, we can just, because these are the magnitudes are equal, both FA and FC are equal forces, so we can just also write there directly. And FD was our K Q square upon 2A square plus our FR will be equal to square root of 2, and this comes as K Q square upon A square. So we can write total force F will be equal to, we can just sort it out, this is Q square upon A square, and this comes as square root of 2 plus 1 by 2. Okay. And for equilibrium, our force F should be equal to force due to tension. Okay. So we can write this as force F, we already know, is our K Q square upon A square, square root of 2 plus 1 by 2 is equal to 2 gamma multiplied by A. And we have to know it as it is soap bubble, so the tension force will be twice. Now we can just solve it, and we are interested in finding out our, basically we are going to find out A, make a comparison with the given value of A, formula for A, and from here we are going to find out N. So therefore we can say that our A cube will be equal to, this comes as K Q square, and this is 2 gamma and root 2 plus 1 by 2. And we can write our A is equal to K Q square 2 gamma square root of 2 plus 1 by 2 and whole raised to power 1 by 3. And we can write this as our A is equal to K prime, and this can be written as Q square upon gamma whole raised to power 1 by 3. Because here we can say k prime is a constant, and the value of constant we can write this as k by 2 square root of 2 plus 1 by 2 and whole raised to power 1 by 3, because this value is entirely constant value. And we can compare it with the given value of a. So we are given that the given a is our k q square gamma whole raised to power 1 by n is equal to k prime q square gamma whole raised to power 1 by 3, and this simply gives us that value of n is equal to 3. So value of n is equal to 3. Next question. It was asked in the year 2011, and it is straightforward. Which of the following statements is or are correct? So in the first case, it states that our electric field varies as r raised to power minus 2.5 instead of r raised to power minus 2. So we have to check whether Gauss law is valid or not. So we can say for option A, and option A, it is saying that electric field is our k is suppose any constant, and it varies with our r raised to power 2.5. And we can find out the flux based on this given equation. So we can say our flux for a closed surface will be equal to our E multiplied by our small area, and we can just write this as E of r, and d will be equal to our d of A is equal to 4 pi r square for a closed surface. E of r we already know is our k upon r 2.5, and this comes as 4 pi r square, which gives us 4 pi k r raised to power minus 0.5. So this tells us that our flux is dependent on r, is dependent on r. Okay, sign everything we are not worried about, we are only worried that it dependent upon r. But Gauss law states that flux is only dependent upon the enclosed charge, that is q upon epsilon naught basically constant. So you can say that but by Gauss law our flux is equal to q enclosed divided by epsilon naught. Okay? So it means not on radius. Thus we can say that option A is incorrect. Option A is incorrect. Part B, or rather we can say option B. And it states that can be used to calculate the electric distribution around a electric dipole. Let us consider a dipole. Dipole means we are going to have two charges, equal and opposite charges. So you can say for electric dipole, we are going to have plus q and minus q. Therefore, charge enclosed will be equal to Q enclosed. This is our plus Q minus Q is equal to 0. Therefore, Gauss law gives us charged enclosed divided by epsilon naught. This comes as 0. Okay. So therefore, it says that it doesn't provide any information about how the field is distributed. Okay. So it cannot be used to calculate the dipole field directly. We can say it gives no information, provides no information about field. So option B is incorrect. B is incorrect. Option C, it states that if the electric field between 2 point charges is 0 somewhere, then the sign of the two charges is same. So it basically means that if there are two charges, let us suppose Q1 and Q2, and it says that somewhere the electric field is 0. Yeah, somewhere it is given as 0. So option C, let us consider 2 point charges. Q1 and Q2, and separated by a distance d. And we have to remember they are given same sign. Okay, so same sign means either both will be positive or both will be negative. 2 point charges Q1 and Q2 separated by a distance d. D. And we consider point P at a distance x from Q1. Therefore, we need to find out that our net field at P should be equal to 0. So which basically means our E1 should be equal to our E2, and from here we can write our K magnitude of Q1 divided by our x square is equal to K magnitude of Q2 divided by d minus x whole square. Okay. And this we can say that is going to give us a real solution because of the quadratic nature if the electric field point is in opposite direction. Okay. So we can say this equation is a real solution if our electric field, let me write it, if electric fields point in opposite direction. And which is only possible, so basically means the electric field should be in opposite direction. So it means one should be like this and other should be in this direction. Okay, and this is only possible if they have same sign, either positive or negative. This is only possible if the charges have same sign, which means either positive or negative. Okay. So if the signs are opposite, the field with add, they will not cancel. Basically premise is that. You can say if sign is opposite, fields will add, not cancel. So therefore option C is correct. And finally it states that the work done by the external force is moving a unit charge, positive charge, from point A at potential VA to point B at potential VB is VB minus VA. So option C is correct. And we need to find the work done. So formula for the work done is quite straightforward. So we have option D, and we can say work done W is our charge multiplied by the potential difference between the 2 points. Charge is given as unit positive, so we can say our work done will be equal to plus 1 VB minus VA, which gives us that work done is equal to VB minus VA. So therefore option D is also correct. D is correct. Next question. It was asked in the year 2011, and it states that a spherical shell, a metal shell A of radius RA, a solid metal sphere B of radius RB, which is less than RA, are kept far apart and each is given a charge plus Q. Now they are connected by a thin metal wire. Then we have to check which of these options are correct. And here we have a shell A and sphere B, and both are having same charge. So initially we have a metal shell. So this is a shell A, radius RA, and charge is given to it as plus Q, and this is our shell A. Then we have a sphere B, so this is our radius B, a charge is also given as plus Q, and this is our sphere B. And then both are connected through a wire. So they are connected with a thin wire, and this is our A and this is our B. So as soon as they are connected with a thin wire, the charge are going to redistribute itself such that the potential, they have the same potential, okay, or we can say same electric potential, same electric potential. So we can write potential on A. So we can say conducting shell which is our A, we can write its potential VA will be equal to 1 upon 4 pi epsilon naught. Let us suppose charge is given as QA. Later we can equate it with Q, and radius is our RA. And for sphere, which is a B, and for that also we can write our VB is equal to 1 upon 4 pi epsilon naught. This is our QB upon RB. And when they are connected with each other, so you can say after connection, VA should be equal to VB. So we can just equate them, and we will get from here 1 upon 4 pi epsilon naught QA upon RA is equal to 1 upon 4 pi epsilon naught, and we have QB upon RB. 1 upon 4 pi epsilon naught cancels out. So from here we get that our QA upon QB is equal to RA upon RB. But we are given that our RA is greater than our RB, so which we can say that QA upon QB is greater than 1, giving us QA is greater than QB. So it means more charge shift to the larger cell. This is the basic meaning of that. Now we come to the options that are given to us. So we start with option A. And we have to remember that the spherical metal shell and solid metal shell both are conducting, and whenever there is a conducting, the electric field inside is equal to 0. So option A is correct automatically. So we can say A is conductor. Therefore, electric field inside A will be equal to 0. Option A is correct. And we just found out our QA is greater than QB, so option B is also correct. Option B is correct. Option C, we are interested in charge density. Option C, we have our charge density, that is sigma is equal to total charge divided by 4 pi r square. So we can divide into sigma A and QA, sigma B and QB. So we can write this as sigma A will be equal to QA upon 4 pi RA square, and sigma B is equal to QB 4 pi RB square, and we find out the ratio sigma A upon sigma B, and this gives us QA upon 4 pi RA square, QB upon 4 pi RB square. 4 pi cancels out, and this comes as QA upon QB multiplied by RB square upon RA square. And we derived one relationship, this one. So we just substitute it, and we can say but QB upon QA is equal to RB upon RA. So we can write that sigma B upon sigma A will be equal to RB upon RA multiplied by RA square divided by RB square, and this square cancel out. So this comes as RA upon RB. So we can write our sigma B upon sigma A is equal to RA upon RB. So we have sigma A upon sigma, okay, I've written it in reverse. So we need sigma A upon sigma B. Let me correct it. So we need this as sigma A upon sigma B is equal to RB upon RA. So option number C is also correct. C is correct. We come to final option, that is option D. And it states that electric field on surface of A is less than that of surface on B. And for that we already know the formula that electric field is our sigma upon epsilon naught, and this is just outside the conductor. We have to remember it. Okay. So therefore we can say electric field at A will be equal to sigma A upon epsilon naught, and electric field at B is equal to sigma B upon epsilon naught. We find out the ratio. So we get this as our EB upon EA is equal to sigma B upon epsilon naught sigma A upon epsilon naught. Epsilon naught cancels out. This comes as sigma B upon sigma A, and sigma B upon sigma A we know is our RA upon RB, and we are given that our RA is greater than RB. Therefore we can write that electric field at B is greater than electric field at A. Okay. And please remember, this is at surface. So option D is also correct. Option D is correct. So I think this was the last one. Yes. So these were the questions which were asked in the year 2006, 8, 9, 10 and 11. And total question were 11. So these complete all the 11 questions. Thank you.